Well, good afternoon, everyone. Thank you for joining our webinar today. This is Carrie Williams. I am the Director of Marketing for Test Oil, and I'm happy to be here presenting with Jim Hannon, who is in ExxonMobil, and he is going to be talking about the influence of base oil on varnish formation. I need to make sure I'm showing my screen. Oops. Can everyone let me know if they can see my screen right now? If you can, please click on the raising your hand icon on the toolbar for the GoToMeeting application on the right. So if you see my screen, okay, I got some hands, good, okay. So before we start with Jim, I'm gonna go ahead and do a little bit more housekeeping. Just so you know, everybody will be on mute today. We do this so I can record the webinar and send it out to you later. So we keep it very nice and clean by keeping everybody on mute. Now, if you have questions throughout the webinar, you can use the GoToMeeting toolbar, and there is a question section. If you enter your questions down there, I will moderate at the end and ask Jim the question so he can get you some answers. Now, if we run out of time or if your questions are too technical in nature, we will hold them for email. So Jim will be able to email you answers. That's all I have for housekeeping. I'll go ahead and introduce Jim. As I mentioned, he is with ExxonMobil. He is the Mobile Industrial Product Technical Advisor for the Americas that supports turbine, hydraulic, and marine oil. He is a graduate of Massachusetts Maritime Academy and has worked in the power generation and marine industries since 1984. I have had the pleasure of working with Jim for the last several months, coordinating everything to get this webinar together. I'm so glad to be here today to be his hostess. And with that, I'm going to go ahead and pass it over to you, Jim. When you're ready, just let me know and we'll start moving along.
All right. Well, thank you very much, Carrie, and appreciate everybody taking time from their day to join this call. And also appreciate Test Oil giving us a forum to have this good discussion, and part of this is that there's always continued learning relative to oils and also testing. And so as we kind of progress with our oils in different applications, we continue to learn different aspects of oil analysis and visual inspection and get a better assessment as to what is an expected life expectancy or service oil interval for an oil. And so there are always a lot of good questions being asked, and sometimes I've seen kind of some misinformation about certain aspects of an oil or filtration, and so it's my hope to go through this presentation and talk to you about base oils and also talk to you about maybe some misconceptions that are out there, and at least give you the point of view from ExxonMobil's perspective, and really just much introduce the idea that if you had any questions, concerns, or thoughts in a different direction, we're wide open to hearing from you and better understanding that maybe there's something we could be improving our ideas on, whether it's the oil analysis side or whether it's the chemistry that we're bringing to the table. So that's kind of the background of why we put this deck together to help kind of talk through that. So if you wouldn't mind, Carrie, if you go to the next slide. And so what I'm going to talk about is the principles of a balanced formulation, and then some rig testing we've done. ExxonMobil prides ourselves on our test rigs. Our rigs are designed to accelerate the aging of an oil in a controlled environment where we can learn oil analysis and visual inspection. And then we've actually got a rig that has a servo valve in it that actually we try to make stick. And that's a very good indication that our oil has got to the point where we're not going to be able to provide reliable service. We've also done some aging studies, and that's some glassware tests that we did at our LTS facility up in Sarnia, Canada, ExxonMobil does a lot of in-depth oil analysis there. And then I did want to offer a conversation about electrostatic spark discharge. There's a lot of, I think, misinformation out in the field about ESD, and we've done quite a bit of study work on it and have our conclusions. And I just put it out there. If they differ with what you've seen in the field, we'd certainly like to hear that and get a better appreciation. I do want to talk to you about some actual field experience, especially when we start talking about the different base oils, because there is a misconception on base oils as well, and I kind of wanted to work through that. And then lastly, I wanted to finish up with varnish prediction and labs like Test Oil that do a phenomenal job with oil analysis. It comes down to the interpretation of the data. And so I think we collectively win from a customer base to be able to provide guidance on that oil analysis that is meaningful and keeps the equipment, in operating at peak operating conditions. And then we'll have a summary. So if you go to the next slide. So, and then I'll skip this. Principles of a balanced formulation is the next group. So the next one that has our spider chart on it. Our spider chart is a way that we can visually demonstrate the quality of an oil. This one in particular is the quality of a turbine oil. So we have these key elements that we strive to be at a 10 out of a 0 through 10 scale. And so we have rust and corrosion, we've got air separability, we've got demulsibility, we've got oxidation stability, we've got foam control, and we've got deposit control. And those are the key elements that we look to strive for our turbine oils. And to get there, we use the right base oils and the right additives blended in the right manner and delivered without contamination. And with that, you set the stage for a long service life for your turbine oil. So if you go to the next slide, Carrie. So this is just kind of a reminder about the different base oils. And the reason I bring it up is there has been talk in the past, and I've been on calls where people will say, well, I'll tell you the reason we have varnish today, and it's because oil companies moved from a group 1 to a group 2 or group 3, and they kind of throw the varnish conversation at the feet of oil companies that have made a move from a group 1 to a group 2 to a group 3. And a lot of what I'm going to show you today should dispel that conversation, that we've actually gotten greatly improved performance when we have gone to the higher quality, more pure base oils. And so I want to talk through that, but I kind of wanted to set the stage here with this API base stock classification, just so you kind of recognize how these oils are made and then what quantifies an oil being in one category or another. And the other important thing to offer out to you here is within a group 1 or group 2, there are different qualities within these base oils. So you want to select the highest quality group 2 or group 3 base oils. And also, we do see benefit of using co-base oils. So some of our oils are actually blends where we'll use some amount of a group 1 into primarily a group 2 or a group 3, or sometimes we blend in a group 5. And a group 5 is a category of all other, not including groups 1 through 4. So group 5 oils actually help the performance of our final product, and again, we would call them co-base oils. So one thing I want you to consider is when people are talking about, well, what's the base oil type of this oil, oftentimes you're going to get the primary base oil might be a 2 or a 3 or a 1, but they may have secondary base oils, and that's what we do. We use a secondary base oil to help in the total performance of an oil. And in that, with that conversation, what I want to make sure is people can overgeneralize, and they say, well, group 2 oils are less soluble. Okay, but if you add a group 5 oil, you have counteracted that inability for solubility, and now you've got an oil with high oxidation stability and good solubility. So again, just bear in mind when you're talking about the different oils that are out there that they might be using co-base oils, and then also the additives that are used with them should be specific to that oil combination and give that optimum performance. Okay, Carrie, we go to the next. We're going to rig testing is our next conversation. And so if you go to the slide that says proprietary valve rig test, and this is, we call it in-house, we call it our DVRT. It's the valve varnish rig test. And we've been doing rig tests for probably 30 years on the industrial side. And like I said, it's a way of accelerating the aging of an oil, but it does allow us to look at the oil, and it allows us to look at the components. And one of the things we did with this particular rig is we put a climate-controlled chamber. We keep that at 32 degrees F or 0 degrees C. And the reason we want it climate-controlled is we know when varnish happens, when products of oxidation happen, and then they tend to plate out or come out of solution when the oil cools. So that's what we've done here is we put this servo valve in this climate-controlled chamber like a refrigerator, and that way we can accelerate the servo valve sticking, and that's in essence what we were looking to do. We also run this rig like a lot of turbines are run, where we run it for 5 days and we shut it down for 2 days, and then we start it back up. And when we start it back up, that's when we look for that valve sticking, because that's it's very similar to a lot of gas turbine operations that maybe they're down over the weekend, and then Monday morning they go to start the turbine up and the servo valve sticks, and because the oil's been cold all weekend and the products of oxidation have come out of solution and stuck to the servo valves. So if you go to the next slide, Carrie, this is just a picture of what that servo valve internals look like. And you can see just the sliding forces, the land, as it's described, as that slides back and forth. If the land sticks, then the servo valve doesn't move, and then the turbine can't start up, whether it's controlling the fuel or the air. And so these servo valves, specifically on the GE turbines, are using the same oil that's in the turbine oil reservoir. And so that you're asking that oil to do a lot, to be a turbine oil and a hydraulic oil, and to use these tight tolerance, 3 micron tolerant servo valves. So we put the servo valve in this chamber, and then we look for, through voltage, we look for sticking of that servo valve. So the graph on the right shows the purple line is what we would like to see, expect to see from a new valve in new oil, and that means it goes to position and it stays there. And the blue line is more of a hunting, where it's seeking to find that set position, but it overshoots and undershoots, and that causes, basically when it would overshoot or undershoot to too wide of a degree, it's going to cause that unit to trip offline because it's not, the servo valve's not hitting set point. Okay, Carrie? Next slide is, in addition to the servo valve, we are also doing oil analysis. So we're doing ultracentrifuge, we're doing MPC, we're doing ruler as far as oxidation and varnish deposit related tests. But we're also doing physical inspection. So on certain frequencies, the components are, the oil's drained out and the reservoir is inspected. And so to the lower right, you can see a good clean reservoir, and then you can see where that varnish is plated out in an in-service reservoir when that oil is hit close to end of life. And the same kind of thing we see on the filters as we're aging that oil. So go ahead, Carrie, to the next slide. So this is an eye-opener a number of years back when a lot of people and different people that have been in the industry for a long time, they were saying it's the companies moved to the Group 2 and Group 3 oils. And I can tell from personal experience that within ExxonMobil, we had some good Group 1 oils that did a nice job, but boy, they had a tough time with those servo valves. So they didn't last long at all in the field, and I had a lot of experience where they basically last about a year before we were having servo valve sticking. So this is the test data from 3 different types. And again, it's the primary base oil. It's not the complete base oil. So I've got the Group 3 in red, and then I've got a Group 2 in the light blue and a Group 1 in the dark blue. And so this testing allowed us to confirm basically what we were seeing in the field, that the Group 3 oil with the high quality additives in us, actually some co-base oils to help the solubility, gives us much greater performance than what we were experiencing in our Group 1 oil from 20, 30 years ago. Okay, thank you, Carrie. Next slide. So also confirming this, we did an aging study. And I'll go to the next slide. Basically, the aging study was a way to age that oil, and we did it through an adjusted, modified D943, which is the toast test. And then what I'm going to do is we ran it at elevated temperatures and a different catalyst to help us get to this data. So if you go to the next slide, Carrie, this slide just shows a comparison of 2 different oils. An oil that's a Group 1-2 blend that's in the market, and then an oil that's a Group 3. And what we were doing, we were looking at all these different oil analysis techniques or tests that are out there and trying to decide what gives us the best insight and the most accurate insight. So we compared, and the testing are duplicate of each other, but we compared linear sweep voltammetry, which is also in the field known as ruler. And in doing so, we compared both amine and phenol, and a percentage versus new. And then we did MPC, membrane patch colorimetry testing, and we looked at the delta E, the change in energy. And then we looked at ultracentrifuge rating. That's where you spin that oil at 17,500 RPM for a half hour, and you look at deposits. Then we did FTIR for oxidation. We did acid number. We did RPVOT. We did HPDSC, which is high pressure differential scan colorimetry, as just another look to see if there's a chance that this test would tell us something different than the other test did. A lot of people like this test because you can use a low amount of sample and it can be run pretty quickly. And then last we also looked at color. So it was kind of interesting as we worked through the test data and we looked at the service hours, and just not to spend a lot of time on these numbers, but if you look at the service hours of the Group 1, Group 2 blend, we kind of were looking at when we had 2 or more tests at a conditional limit, that's when we started getting into a caution. So let's say the group 1, group 2, when we got to 1,344 hours, we could see the MPC jumped to a 41. And I guess to work through it fully, as you can see that amine and phenol were still fine. So oxidation stability, the antioxidant was still there, but now we were starting to see that MPC jump on us. We see the UC go to a 4, which is concerning. FTIR for oxidation stayed at a 1. Acid number stayed. RPVOT actually had an increase, and that's just the nature of RPVOT testing. We did see the HPDSC jump to actually drop to a 16, so that was kind of in its caution limits as well. And then color went to a 3, and then you start looking over at the group 3 oil, and we didn't see things starting to manifest until we hit like over 4,000 hours. So now you can go from the group 1, 2, we were kind of looking at trouble at about 1,300 hours, and now we're at 4,000 hours in probably over 5,000 hours. And you could argue that this oil was still in good shape because even though the amine was down at 17%, the phenol was totally gone, everything else was kind of lining up pretty nicely. Like the MPC was looking good, the UC was looking good, FTIR was good, RPVOT was nice and stable. We started to see that HPDSC had dropped, and then we started to see a darker color, a D8. But anyway, this just kind of helps us with our story of, hey, we're making a better oil in this with a group 3 as the primary base oil than we had been with a group 1, 2 blend. So Carrie, if you go to the next slide. So now we're going to, and I don't know this audience on the line if you're too concerned about it, but others have been concerned, and I think the conversation has kind of died down over the last few years, but there was a period of time that a lot of people were very concerned about electrostatic spark discharge. So I'm just going to talk you through it real quickly here. If you go to the next slide, Carrie, slide 15, there is some guidance out there by API RP 2003, the influence of conductivity. And basically, their summation, and this is based on fuels, but we saw the same thing in oil, is they consider the oil to have low conductivity if it's below 50 picosiemens per meter, and high conductivity if it's above 50 picosiemens per meter. And so it is a good kind of go, no-go for us as far as what external agencies consider high conductivity and low conductivity. And then the story with that is higher, well, generally liquids with greater conductivity, 50 picosiemens per meter, do not accumulate static charge. So they dissipate that charge, and you get less chance of causing a spark as you're going through filter or going through your system. So if you go to the next slide, Carrie, I'm on slide 16. One of the things that I've seen written about and blatantly incorrect is that people were blaming the base oils, and they were saying, well, you've got high spark because you've moved to a different base oil. And we did a lot of testing to diffuse that conversation and say, hey, it's not about the test oil, or it's not about the base oil, it's about the additive. And so you can look down the table on the right. These are ISO 32 turbine oils, and they're all of different primary base oils. And again, it's a primary base oil. I don't know the complete package of a lot of these oils, but you can see groups 1, 2, 3, and group 4 represented. And basically, a lot of them are fairly low in the conductivity, which would mean maybe a high potential for spark. But the influence of the base oil was minimal, you can tell, like if you go down to oil G, that's a group 2 that has an extremely high conductivity at 286 compared to the others, and that's all about the additives. The additives used there just allow for conductivity. Same can be said about like oil K is a 111, and then that's about the additives. It's not about the base oil at all. And then in comparison on the hydraulic oil side of things, I just put this in here as well. There was some conversation that, oh, if you go to a non-zinc hydraulic oil, you're going to have spark. And the point I make here is that, hey, here's a non-zinc hydraulic oil that tests out at 119, and that's well above that 50 picosiemens per meter threshold that API points out. So if you go to the next slide, Carrie, and unfortunately we can't show you this video because I couldn't connect through PowerPoint on this presentation, but there's a video that if you catch me, I can explain it to you, or we've talked about it. Basically, we did some work with Hilco on some spark tests, and we put in what we would consider a low conductivity oil, and that sparks like crazy through filters, and it has to do with if you have the oil cold, if you have high velocity, and you have low micron rating, and then a steel back filter, you're going to get that oil to spark, and it's basically a kind of a lightning show, and it's kind of interesting, and you can hear the popping noise, and that's pretty neat. Then we put in an oil that had high conductivity. Its conductivity was 111, and that oil ran through the same system, and you couldn't hear a thing. You couldn't make it spark. So it did show you the influence of conductivity for making spark. But what we would say is, again, it's the we haven't seen where conductivity has actually impacted the oil's life. So we see it as a spark problem if a turbine is kept on turning gear for an extended period of time and the oil is cold and you can hear the sparking. Well, yes, that sounds like a problem and should be addressed in that way. But I would say 95% of the applications, turbines are not in turning gear for a prolonged period of time, and normally that's a transient condition that as soon as you're up to temperature, that sparking goes away. So, Carrie, I'm on slide 18. I just wanted to point out real quickly the influence of base oil. And so what we did in this testing here was we had different base oils, group 1, group 2, group 3, and these are unadditized base oil, and we ran some testing, and you can see they all unadditized, they all have a conductivity of 1 or less than 1. So again, the influence of conductivity is not the base oil, it's the additives. And then in parallel, there was a lot of people saying, well, it's really water that drives conductivity. So we had our LTS lab do some additional testing where we took a turbine oil and we spiked it with water. So you can see the first column there, we spiked it 100 ppm and we measured 61 and we get a conductivity of 28. Then we spiked it with 200 ppm and we get a conductivity of 24. Then we spiked it with 812 ppm, approximating 1,000, and the conductivity stayed the same at 24, and then 2,000 ppm, it's at 22. So it was pretty interesting. All the way up to 2,000 ppm, minimal impact on conductivity. So anyway, this is more just kind of a theoretical study that was done just to kind of understand the influence of conductivity on the oils. If we're going to move on, I'm going to talk about field experience, and we'll go to slide 20. So, and again, this is the influence of base oil on turbine oils. And this example is some GE Frame 7 EA turbines. And so these guys started out with a Group 1 oil in 1992. And this Group 1 oil, after about a year's period of time, 6,000 operating hours, they were starting to see servo valves sticking. And they were really struggling with this, and it was a problem because come Monday morning when they go to start up the turbines, the servo valve would stick, and it would cause them 6 hours of downtime, and it was an issue for them. So they started their varnish mitigation was they started doing frequent servo valve and last chance filter changes to get through this. So then we worked with them, and we brought to them a primarily Group 2 oil, and we did better. We got up to 3 years, 18,000 hours, and they were pretty pleased, but we still had those same kind of issues. So then, 2009, we brought to them a primary Group 1 oil, and guess what? No servo valve sticking. We're going 8.5 years, 46,000 hours, and going. There's no varnish mitigating strategy. So again, just kind of proves to us our rig testing, our aging study, that as we progress in higher quality base oils with the right co-base oils and the right additives, that we can really improve the performance that we'd had in the past. So then if you go to slide 21, just another example of where we were with a Group 1 oil, and that Group 1 oil at about 20,000 hours, this is on a Frame 7 FA, was starting to have those servo valve sticks. And then we did a flush, and we changed them over to a Group 2 oil. And as I say, so far so good. And this oil's doing extremely well. No varnish mitigating. The customer's happy, and he doesn't even see the need to change it out at 65,000 hours. So we're very pleased with that level of service. And the other element to point out, this Group 1 oil has what we would consider low conductivity. It's below 50 or 60, it's below 60 picosiemens per meter, and it tests out at around 16. So there's some people that would tell you that, hey, if you've got low conductivity, you're going to create spark, and you're going to have a short life of your oil because it's the cause of all varnish. And just that has not been our experience. And here's, proof in the pudding that we've got 2 turbines running side by side that are now over 65,000 hours, and those servo valves sticking. So here's some test data from that particular site, and we've got these 2 different units, 7 and 8, and you can just kind of flash through some of the data here. Nothing really too exciting. I would point out that like our ruler numbers in this particular oil, and this is just another good point to talk to you about, is most oils use a combination of amine and phenolic additive for the antioxidant. And by design, that phenolic will convert into an intermediate that actually helps support that aminic antioxidant. So we know and expect our phenolic to go to 0. And so there are some people out there that said, oh, that's problematic, and you should be changing your oil or sweetening your oil or something to that extent. And we are extremely confident in saying, hey, in that oil, when our phenol goes to 0, we expect it, and it's doing what we expect to see. So here's this oil with 65,000 hours in it, and our amine is still around 50%, and our phenol is down at 0, and it's behaving just as we would expect it to be. And the customer is pretty darn pleased and is going to continue to run this oil until, I guess, bad things start to happen. But at this point in time, based on the data and his performance, that they're pretty pleased with how this oil is functioning. So, Carrie, if you go to the next slide, slide 23, this is just a little bit of a story about a Frame 7 FA that started at a Group 1, then it went to a Group 2, and then it went to a Group 3. And this is the transition time. That in 1998, it started with a 1. Then in the late 90s, it moved to a Group 3. And during this time frame, they were doing varnish mitigation. And their basic thing was they started using electrical heat tape on the hydraulic lines to keep those lines heated as a way to minimize that products of oxidation plating out. And then so 2010, they transitioned into this primary Group 3 oil. And to date, no servo valve sticks, no varnish mitigation, and good service life. They're well above that 64,000 hour, which is the GE overhaul to overhaul time frame. And so that's kind of a major milestone for us and for most people in the industry, is to go from overhaul to overhaul without being concerned about having to change your oil. Slide 24 is an example of using a Group 4 oil. And this used to be a Group 1 oil in these Frame 6Bs, and they were having servo valve issues at about 13,000 operating hours. And then they moved to a Group 4 oil and had done extremely well for 9 years, over 65,000 hours. Again, so just another indication that when we moved and we went to upgraded base oil, we've actually done a lot better, contrary to some people's belief that they were better off in the old days. So Carrie, I will go to varnish prediction is the next topic. And so slide 26 is a picture of different components within a hydraulic system. And this is, on the left, is the last chance filters that would be used in a GE equipment. And then on the right is the servo valve itself. And that servo valve is two key elements, the pencil filter and the spool piece. And so one thing our lube engineers and sales engineers are very good at doing is working with their customers to actually do physical visual inspection to confirm oil analysis. And you can tell real quickly whether you're having a problem based on a visual inspection as a way to confirm the oil analysis that you're seeing. So Carrie, if you go to slide 27, this is after a lot of different testing and a lot of different methodology, whether it was the rig testing, the aging testing, the field testing, we've kind of come to our internal ExxonMobil suggested limits for our products. We can't speak for other products, but these are the ones we use in-house. And a lot of this is actually based on ASTM D4378 recommendations, and we are very involved in the writing of those standards as well. But we look at, when you do oil analysis, that you really can't rely on one test alone, and we look at a multitude of tests, and our confidence is in these tests. So the ruler testing or linear sweep voltammetry, when we get to 25% of our initial value of the aminic is when we get to a caution limit. It's not a panic limit, it's a caution limit. And we expected our secondary antioxidant to go to 0, and that is not a concern when the phenol drops to 0. It's the amine that we've got our eyes on. Then for MPC, membrane patch colorimetry, and the important thing is to look at the delta E, change in energy rating for us. And then if you use a scale, that's okay. That's good for a scale, but just appreciate it can be represented in either delta E or a 0 to 100 scale. But our experience has been when we see when we see 40 or greater, that's a time to look at it as a caution. When we go to ultracentrifuge, where we spin that oil, we look at a scale of 1 through 8, and we start to caution when we hit a scale of 4 or greater. We also look at FTIR for oxidation, and that the concern level we hit is a 4 or greater. Acid number, our oils typically start with an acid number about 0.1. We've got one oil that starts at about a 0.2. But when we start hitting about a 0.4 or greater for acid number, we put that as a caution as well. And lastly, RPVOT, that some people say isn't needed anymore. We've seen on a number of occasions where RPVOT and acid number were the only things that told us we had a problem. Everything else looked very good, and we would have fooled ourselves by not looking at RPVOT. So we still believe that RPVOT has a home and should be tested, maybe not quarterly, but more of on a annual basis or every 2-year kind of basis. But that's really up to the customer and up to the sensitivity of the equipment, that type of thing. So we recommend all these tests be run. And then what we've said is, hey, when you get 2 or more of these at a caution, then let's start talking about the potential of what's our next step here. Are we talking about maybe a bleed and feed where we sweeten it up a little bit to get to an overhaul? Are we thinking about an oil change, that kind of thing? But the other element in there is we want this interpretation to be application specific. So we know that the GE turbines that have the servo valves that are part of the integral hydraulic system are more of a concern than maybe another turbine that doesn't have servo valves and is just, the oil is just doing the job of supporting the bearings, which is the primary function of the oil. But the tolerances or the clearances of those bearings might be in a 30 microns, which is quite a bit wider than what you're seeing in those servo valves. So understanding the application is key. And then also understanding if you can have the opportunity to do any kind of inspection, that also helps tell the story. And then lastly is to have the operating hours, to understand, is this oil at 10,000 hours or 60,000 hours? And that's going to help drive the discussion about what's our next step here. So there's a lot on that slide and a lot of good conversation, and we look to a lot of good feedback on it. And so we'll take it, Carrie, to the kind of the summary slide, the next one. And so this is a quick summary on it. Much is being said about the influence of base oils. I feel that it's too general and often incorrect. Select high-quality base oils used with the proper additives offer greatly improved performance. Turbine oil conductivity is primarily influenced by additives. It's not the base oil. Turbine oil varnish is not influenced by conductivity. We've proved that out in many, many applications. And then test rigs, lab testing, field experience clearly show higher quality base oils blended with the right additive technology get you greatly improved performance. And then lastly, oil service hours, visual inspection, and the right oil analysis can readily improve reliability. So I do again appreciate your time to listen on the subject, and mostly I appreciate any feedback, anything that you think you've seen a little bit different, or anything you wanted to talk about more. I'd like to have those conversations. So, Carrie, thanks again for letting me run this, and if you had any questions, please let me know.
Well, thank you, Jim. I do have some quick questions here. We have just a bit of time left, but I'll try to get to some of these. So Scott is asking a technical question. He says, how relevant would you say varnish resistance is to units? Let's limit this to steam turbines. which have a separate hydraulic system, typically fire coils, sorry. In our experience, varnishing in these circumstances has been a nuisance only, requiring additional equipment cleanup on outages.
Right. So it sounds like a question really tied to the EHC, the electrohydraulic control system, which would be using that phosphate ester. And I've seen, again, the phosphate ester is not our product per se, but I have seen some good technology, including electrostatic precipitators, help those systems. So I think that's his question. As far as the steam turbine itself, by and large, we're using some of, you'd say maybe our circulating oils and steam turbines and getting long life, 20, 30 years. So the steam turbines typically are not oxidizing the oil to a point that it's creating a great deal of varnish. You can see when you go down for overhaul, there's some mild varnish, but so the varnish would be really of a concern if it starts to retard heat transfer in the bearing. It causes a bearing overheating, and you can see that in your bearing temperatures, and or maybe it translates into a vibration. But largely, varnish in steam turbines is not a large concern.
Okay, thank you. One other question from Phil. He says, on slide 13, why wouldn't the MPC and UC rating continue to increase past the 1344 hours in the group 1 and 2 blend? Why did the number go down? Sweetening from additional oil being added, question mark?
No, so there was no sweetening, and I'm going to go back to that slide real quick to take a look at it myself. So these oils just continued to be aged, and you're right. So I went from a 41 to a 34 to a 44, and then my UC actually went up to a 4 and then back down to a 3. And in the world of oil analysis, we know that there's some variability, and oftentimes we would look at that 41 is close enough to the 34. It's just showing that, yeah, we're starting to pick it up. So when you start interpreting this data, you kind of put it in the same general category. The 41 is pretty close to the 34, and you can just say that, all right, we're starting to play it out, or starting to build products of oxidation. So they're pretty much in a similar camp. Maybe you could say, well, why did we go from a 6 to a 3? Sometimes products of oxidations can drop out of solution and maybe not be in that test tube when we ran that sample. So that would be the explanations there.
Okay, let's do one more. I have Pat asking, in a hydraulic system that is loaded with varnish, are there varnish cleaners or removers on the market that will clean this up, that will clean up the system?
There are, and we've seen some that we offer, and we've seen that there are others out there in the industry that seem to do a pretty nice job. And so they're added at certain concentrations, 5 to 10% along those lines. And what it does is it can, kind of like when we're formulating a base oil, we want to have good solubility. And what this cleaner can do is help on that solubility, but what it does is it can impact other performance features of the oil, like foam and emulsibility and long-term oxidation stability. So when we do use them, we use them in a short-term process where we wouldn't want to continue to use that turbine oil or hydraulic oil system for a prolonged period of time, fearing that we would cause more harm than good. So they have been used to help clean up the system, do a drain, flush, and refill, and you set yourself up for, you know, many future years of good service by using those cleaners to help you, you know, break through the bad condition you're in.
Okay, I have one more question. This is from Larry. He says, what is your experience with using resin-based ion exchange filtration for varnish mitigation? I have found the electrostatic units temperamental and depth media only sufficient with cold filtering.
Right. Well, those are very good observations, Larry, and very similar to mine as well. Electrostatic seems to do well in the beginning, and then for some reason, and I can't explain it, it doesn't have the long life, long capabilities that I've seen in other technologies. The high depth media works extremely well if you chill it. If you chill the oil before it goes into the high depth media, and so we've seen that in physical examples, and actually we use that same thinking when we built our test rig. Is that's why we chill it, to have those products of oxidation come out of solution and then stick to the high depth media. And one thing we have found with the high depth media is if it was chilled and then you heat that oil back up, everything that you locked into those filters then releases again. So it's good if you keep that at a constant cold temperature. So lastly is the resin technology. And actually one of the real nice things about some of the resin technologies out there is they give different chambers that maybe upstream of resin you would use high depth media. So I've seen some filter systems where you maybe have high depth media then followed by 2 resin beds. And I've seen very good things happen in those kind of applications. So I think your experience is kind of similar to what I've seen in the field as well.
We have time for one more, and I'm not sure if we can answer this because I'm not sure what slide he's referring to. But Josh is asking, are the additive package in all of these the same, with the base oil being the only variable?
And the answer is no. So we use select amine and phenol, and sometimes it's just an amine only. And there are many different types of amines in the market. And so that's one of the things sometimes people say, hey, I can re-additize your oil because I know what amine and phenol ExxonMobil, for example, is using. And we'd say, well, I don't know how you know that, because there are many different options out there. And so we use the combination that works the best for us based on our analytical skills. We do a lot of modeling of different components, and then we take it to our rigs and take it to our glassware testing, and we look for just that proper balance. So these are not just packaged off the shelf that we just plunk into various base oils. So, and then again, remember with those base oils, oftentimes we're using a co-base oil to help even further that performance.
Okay, well, that's all the questions we had. I'm so glad we got to get to all of them. And Jim, thank you again for presenting today. And our goal is to always have educational webinars to share, and so it's so nice to have you as one of our speakers today. And I will go ahead and send a recording of this to everybody who attended, and if you have questions, you can definitely reply to that email that you get, and I'll make sure that Jim gets your questions. Have a great day, everybody. Thanks again, Jim.
Thank you. Thanks, everybody.
All right, bye-bye.